I'm the session chair of today's second session. It's all about digital twins, state-of-the-art use cases and new trends, presented by Carlos Gamal and Sergio Lasso.
Thank you. I'm not used to this kind of microphone, so in case I forget about it and you stop hearing me, just make me a sign so I can put it back to the mouth. Well, the topic of this session will be digital twins, and the session will be divided. The talk will be divided into two parts, and I will be giving the first one. I'm Carlos Canal from IT Software Research Institute and the University of Malaga in Spain. And after the coffee break, the second part will be given by my colleague Sergio Lasso from the Kerku Software Engineering Group and the University of Extremadura, both in Spain. So let's start with it, with this first part. And this is the contents of the talk. Well, first of all, you have in the right this QR code that you can use to download a PDF version of the slides, so you can have them on your laptop or your mobile phone, because some of them have links to the material that is referenced, and the links are not explicitly written in the URLs are not explicitly written in the slides. The contents, okay, I will start with an introduction talking about the current hype, which is around digital twins, and then I start to try to find a consensus on a definition of what a digital twin is and which are its main properties. And I also tell you a brief story of digital twins from their beginning to this current hype on them, and then I will discuss some of the main proposals for an architecture of digital twin, which are the main components and how they are related to each other. After that, I will talk a little bit about different fields of application and so some examples in some of them, and then research opportunities that are currently in the field. And for that, I will focus on three different things, on the different fields. One is composition of digital twins, another one is deployment of digital twins on the cloud to IoT continuum, and also about fidelity assessment of digital twins. And in the end, I will talk briefly about the main technologies and platforms that are used in this field, and just a few hints on it, because Sergio, his talk, will explain far down on this. Well, let's start then. If you go to technical journals, you can find a lot of news talking about digital twins of different things. There are news about NVIDIA digital twin for a robot, digital twins for human organs, digital twins for drug discovery, digital twins for energy consumption, and also for railway movement. You can find a lot of information, a lot of fuss about digital twins, not only in technical journal, but also in general purpose publication papers or magazines. And this, if we go to our field, if we go to research and we ask the BLP about publications that have the term digital twin on their title, you find quite a big number of them. If we group them by year, we can find that this publication started approximately 10 years ago with only a few publications, so 4 in 2016, but they exponentially grow until almost 2,000 publications last year. The figure for this year is low, because only I took this snapshot at the beginning of the year, so probably it is much bigger now than it was before. So there is this hype, not only in the news, but only in the research community that is working on and publishing on this topic. And if we go to, instead of BLP, if we go to Scopus, we have very similar figures. We have here the curve that shows an exponential growth. Maybe it's decreasing its step. So probably we're approaching the maximum, and okay, let's hope that there is not a big fall down as in many other technology hypes in this field. If we analyze all these publications by the country, we see that the main publisher in this technology is China, followed by Western countries like United States, Germany, United Kingdom, and other European countries. This is no different than any other field, at least in computer science. So we don't get any particular information from that. The interest of digital twins is spread worldwide. And what is a digital twin? Everyone have heard about it, but we have all the same knowledge about what they are, which are the main features of a digital twin, which are the main component that must be in a software system to be considered a digital twin. Okay, we can ask someone informed, and I did that. I asked ChatGPT what a digital twin was, and its answer was this one, but it was a little bit longer than this one. This can be reproduced easily. It was a couple of weeks ago. I don't think it has changed too much. And said that a digital twin is a virtual representation of a physical object or a system or process that is continuously updated with real-time data. The digital twin mirrors the physical counterpart as accurately as possible, and is used to monitor performance, predict outcomes, and support decision making. This is a good definition, and we can agree on it. It has the main element of what a digital twin is, and it also goes on explaining what are the main features of digital twins. First, the use of real-time data. The digital twin uses sensors and other sources of data to stay synchronized with the physical object, with the physical counterpart. It also is able to perform simulation, though it's not only synchronized, but we can use the digital twin to predict what would happen in certain situations that may occur in the future, and that maybe we want to avoid, or maybe we want to enforce. So we can use the digital twin can be used for simulation. It can be used also for analytics, for explaining what happened in the past. From taking historical data on the physical element, and it's not only used for the production stage of the physical object, but it tries to cover all the process of the life cycle of the physical object, from its design to its operation and also its maintenance. If instead of ChatGPT we asked other LLM model, LLM system like Gemini, Pilot, or DeepSeek, we will find very similar answers to this question. And this may suggest even that okay, they are basically the same model and LLM model, and using the same data coming publicly from the internet. But the answers are so similar that you may think that they are copying each other. When we ask DeepSeek, DeepSeek asks ChatGPT and just send us back its answer. And also, if you go to Wikipedia, there in the link, you have almost the same definition. So, as a conclusion of this, I say that if what we are looking for has an entry in Wikipedia, go directly back to Wikipedia, because probably it's a good answer, and it is very much eco-friendly way of finding information. With respect to history, when did we start to use digital twins? In the literature, you very often find that the first digital twin was related to the NASA Apollo 13 mission. That was a mission for sending and a spaceship to the moon with 3 astronauts in it, and then you have the twin. You have in the right, on your right, no, on your left. You have on your left a picture of the capsule flying in the space, and in the right you have the digital twin of this capsule, which is on Earth in Houston in the control center, and there you can find that there are several physical models of the capsule, and also there are very big computers as they were on that time. And also there are several people they are running their computers, and well, what we can see there is that we have improved a lot, both in the size of the computers and also not using switches and ties for doing work in computer science. So at least in that we have improved. If you want to see to read the full story of the mission, you have this link there. If you click in the PDF version, if you click in the hand, you go directly to the source. But what happened there, probably because of the number of the mission 13, is that in their flight to the moon, when they're not that far for arriving there, in the red rectangle, about hour 55 of the mission, there was an explosion of one of the oxygen tanks, and this explosion damaged the capsule, and this explosion also produced a very strong shortage on the oxygen supply of the capsule, and this severely compromised the mission, not only in the sense that this oxygen was used for putting the capsule in movement as an energy source for the capsule, but also as a supply of oxygen for the astronauts. So they needed to abort the mission because it was not possible anymore to arrive to the moon and come back. And when you are in a spacecraft, you cannot simply turn around. They have to, in fact, go to the moon, not land it there, of course, but using the gravitational impulse of the moon for going their way back. And for doing this apparently small changes in the mission, they have to make a lot of adaptation to their plans that they originally have, and they have to do a lot of simulation of what would happen, how could they do this go and return as fast as possible, because they wanted to keep the astronauts alive. In the end, it was a successful mission. They returned to Earth, and okay, this is considered maybe not the first digital twin, because okay, we have these parts, but the communication between them is done. Data from the sensors in the capsule was sent via radio to the control center on Earth, and also the astronauts were saying what was happening there in the capsule, and the information flowing back in the other direction from the control center on Earth, from the digital twin on Earth to the physical object, was sent also by commands or radio commands using human operators. So this communication was performed manually. And what we want to do in a digital twin is that this is synchronization between those elements, the physical and the digital, is automated and in real time. But more or less, we can find that this is we can agree that this is if not the first whole digital twin as we understand now, is the first successful use of a digital twin. Well. The first definition of this concept comes from Michael Greaves in a course that he gave in the University of Michigan. It was about product life cycle management, and he gave a definition of the context and the concept. But the problem was that instead of calling it a digital twin, he used a much less fancy term. He called it mirrored space model, spaces model. So that didn't succeed, but the idea was that he was talking about is what we now understand as a digital twin. The first use of the term was done by another Mike Safto, that he was working in the NASA, and he gave this definition that is there, that, as you can see, is very biased between spaceships. It mentions flying twin, fleet history, and all, but well, it was the first one that published, at least, we can find in a scientific publication the first use of the term, and it was in 2012. 2012, yes. A more general definition, not so biased to spaceship space mission, was given a couple of years later by the same Michael Griff, which is the guy there in the picture, and he simply said that a digital twin is a virtual representation of someone that has been produced. And this links with digital twins, and we'll see later, this links DTs with manufacturing. Is one of the main fields of application, or at least is one of the fields in which more digital twins have been developed until now. This definition is from 2014, and apart from these two, we can find hundreds of definitions. There is even a review of the literature. This is this one which is indicated there, with a companion website when they have all the material they have used for the review. They have reviewed more than 350 papers about digital twins. It was performed, this study 3 years ago, and they have found more than 100 different definitions of what a digital twin is. So we have a lot of different ideas of digital twins are. Just to mention a few of these definitions, some of them they are too vague. It's a digital equivalent of a physical product, so this may be some kind of mock-up, simply. It's not just a replica, it's something more than just a replica of a physical thing. We have also, the second one says this is a simulation method that can be used for evaluation and optimization. So for them, digital twin is just a simulator, any simulation tool, or a model-based representation of entities of the real world, such as machines, cars, and products. Okay, it's not just a model, it's a model that can be used for several things. The core of the digital twin is a model, as we will see, but also it has many other things that are important to be considered something, a model, a digital twin. And of course, simplified numerical models, models can be done of using different theories, and this is a very vague and restrictive definition. Some other definitions are too specific of certain domain. Virtual replica, okay, of the printing software, okay. They are talking about printers, but set of virtual information that fully describes a potential or actual physical production. Okay, up till that, but from the microatomic level to the macro geometrical level. Probably this definition is too ambitious because it wants to represent the full physical object in the digital twin. It's a model, and when we model on a certain purpose, and we make abstraction of all the complexity that is in the thing that we are modeling, that we are not interested in putting all this complexity in our model, only keeping what we are interested in, the features that we are interested in. Virtual model of the physical plant, okay, as production or manufacturing. Software model composed of 3D, physical, mechanical, electrical, along with detailed information about the assembly process and system of production. Okay, you see that many of these definitions come from very specific products or fields of application, and if we have to take one canonical definition of the term, we could use that of there's a digital twin consortium, and these guys has developed even a catalog of terms related to these technologies, and there the definition that they give there is that a digital twin is an integrated data-driven virtual representation of real-world entities and processes, and this representation uses synchronized interaction at a specified frequency and fidelity. Then you find all the elements that are important in a digital twin. It's of course a virtual or digital representation of something that exists, that may be a physical object or maybe just a process or a piece of software. But also this representation is data-driven. It has to be fed with real data coming from the object or the system that we are modeling, that we are representing. And this interaction between these two objects have to be synchronous, have to be done in real time with a certain frequency, because the digital twin is discrete, of course. So we get this information with a given frequency and with a given fidelity. This is why this view of the digital twin of a robotic toy car is pixel, because we may use different fidelities depending on our needs. So this is the canonical definition that we can take for this term, and you have these two main parts, and also the synchronization and transmission of data and information between all of them. In the upper part, all the data coming from the sensors of the physical thing going digital, and in the low part, all the more elaborated information or commands coming from the digital, from after doing maybe some simulation, after taking some decisions to control the physical element. So to sum up and finish with this part of the definition, we could say that it's a sort of quiz, a digital twin is either and you have to fill the gap, a model, a simulation, a dashboard, a control loop, a prediction system, or a machine learning system of its physical counterpart. And okay, what would you say? Is it a model? A digital twin is a model. A digital twin needs to have a model of the physical counterpart of a physical thing, but it's not just a model. It's a model accompanied with several other that are important for being considered a couple of twins. First of all, the model can be executed. The model can be valued, so we can, from several inputs, get an answer, get our response in the sense of some feature of quantity that we want to control. So we can say it's a model executable, so it's some kind of simulation. But it's not only that. Digital twins are also used for having an overview of a complex system, so they are also related to control panels or to dashboard. You have to, for humans to take decisions, to have abstracted information that happen on a complex system, so they are related to dashboard. Or the digital twin usually has a dashboard for human interface. This bi-directional communication of data, of information, it's related also with control systems and control loop, with a closed control loop. And of course I mentioned that we need a model, and for certain kind of systems that are physical systems, we have very good theories for developing models, and we have mathematical models, and we have physical models, and we have models for many things. But maybe for some kind of systems or some kind of particular complex system, we don't have a theory for developing a model. So if we don't know how to build a model, how can we have a twin? Well, we could use prediction system, we could use statistical methods like ARIMA or any of its variants to use historical information coming from the physical part in order to infer the future behavior and build this statistical model of the system without knowing a theory for our system. Or we can use more elaborate machine learning and AI techniques for developing this model with deep learning or whatever. All this can be applied to digital twins when it's difficult to build a reasonable model of our system. So the answer is yes, a digital twin is all these things at the same time, or at least most digital twins have all these elements. So the answer is yes to all. But I would highlight that the physical twin can be not only a physical thing, not only a physical object or entity, but also it may be any kind of system, a software system, a browser, whatever. And an important thing, because many people say, okay, we have developed a digital twin of whatever. Okay, for being a digital twin, there should be asynchronous and two-way communication between the physical and the digital part. And this loop communication must be automated, not like in the Apollo 13 mission that was human performed, but automated. In that case, we would say that digital twin system is a pair of coupled physical and digital twins. Well, let me check that one. Okay, perfect. Well, what are the main properties of digital twin? For this, I will follow a paper from a colleague and good friend from Spain, Elena Navarro, that was here last year presenting a talk on digital twins too. And she made this paper with some other colleagues trying to define which are the main properties that a digital system has. The first one, which says representativeness and contextualization, deals with the flow of information from the physical to the digital. The physical, the digital twin, sorry, must mimic, must follow or reproduce the status of the physical entity, considering only the features that are important for us, that are important in our context, the purpose that we have developed the digital twin for. The second reflection goes the other way around. For understanding what is the current status of the physical thing, we don't need to go to the spaceship and find out what's happening there, but the status of the thing is if the model is good and the transmission of information is good, the status of the physical thing is already in the digital counterpart. So observing the twin, we can find which is the current status of the system that we are modeling. Entanglement refers to the whole communication and said, okay, this communication of data in both directions might be performed in real time or close to real time. Of course, if your physical object is a spacecraft flying to the moon, there is a delay in the communication, but we are always trying to be updated as soon as possible with the status of the physical thing, so both twins evolve at the same time. The fourth, predictability, means that digital twins are not only used for reproducing a physical entity, but also to perform simulation of the behavior of the entity in order to see or determine the outcomes in a likely future context. We can perform simulation and say, okay, if this happens, then the system will behave, the physical system will behave this way. Maybe this is interesting, maybe this is a risk, so we can decide if we want to enforce this behavior or we have to prevent this behavior. There are several more properties. We have gone into the future with the previous one. We can go to the past with persistency and memorization. The digital twin maintains a continuously updated and upgraded virtual representation of physical phenomenon part, so the data must be kept somewhere, and for that we need this kind of memorization of the data that can be used later for performing extra analysis or whatever, or adjust the parameters of the model. For that, digital twins they usually have a database for keeping all the information related to the communication between both twins. Replication is related to the fact that, okay, until now I have always talked about two twins, the physical and the digital, but we can, for any physical system, we can make several models, different models, each one addressing different features of the physical thing. So maybe it's not a pair, we have several siblings. So digital twins may replicate the physical thing in different contexts, each one with a specific purpose, and using particular features of the physical. Composability, we have several twins. Okay, any system can be composed of several parts, or any system is part of a bigger system. That happens also with twins. Digital twins cannot be considered isolated, but maybe we need to combine different twins that have been developed with different people. So composability is one important thing when we are talking about these technologies. And the last one is related with this school. This school is about service-oriented computing. Manageability says that the digital twin must have an API from which we could interact, and not only with the digital system, but only through this API interact with the digital thing in order to control its behavior or to deal with damages or troubles that may happen in the system. These are the main properties, and this is a good work trying to categorize these properties or systems. And if we now go to the architecture, we have here a three-dimensional architecture which was done by this, I need a little bit, some water. We have we have this picture from this Michael Greaves paper, and it has said, okay, this is a conceptual architecture in which we have the three main elements. We have the physical, we have the digital, we have this communication between them. So as a conceptual architecture is okay. But if we wanted to implement it, we will need to add several other elements. So we usually talk on 5 dimensional architectures. This one is from a paper from Tao. Maybe it's not the best picture, but okay, that's what I found. Here we can identify the physical twin, the digital twin, the communication between them, which is a lot of communication channels in this picture, and we have extra elements as the data lake here, which is in the middle, and also has some kind of way of transmitting information from one to the other, but also decoupling, desynchronizing this information, so the information that is taken from the sensors of the digital twin is put in the data lake, and we can do a loosely coupled pair of twins, because this information will be retrieved later when the digital twin needs it. And for implementing this data lake, of course, we use some kind of database system, although the conceptual idea of it is more related with a coordination tuple space, for instance. But for implementing it, we always use a database. There is also an extra element, which is that of, it cannot be seen properly here, but this service part, which is related to the property that I mentioned before, the manageability. And this API should provide different kind of services that can be a user dashboard for controlling and having a overview of the whole system. for data analysis, for detecting anomalies, from making predictive maintenance, whatever. There can several services, but that can be plugged in the digital twin system in order to provide an extra functionality to this just the couple of twins. Of course, there were many definitions. Some there are even more different architecture proposed in the literature. They have here we have only a few of them. This one is the reference architecture for digital twins by the ISO, and here we can find very clearly which are the different elements that I have mentioned before. We have the physical, we have the digital, we have the data lake, or the data between all of them. We have also an entity for representing the connections in the system, and all this part for the user dashboard and the services. So this is a good representation of the typical architecture, five-dimensional architecture of a digital twin. But we have many more here. I'll go quickly through this. Montiarch is an ADL and architecture description language, and someone is mentioned there, has developed this description of the architecture of a digital twin. We still can find all the elements, although in this case the connections are somehow implicit in the links between all those elements. They're not given a first class presence in the system. This is the architecture of Open Twins, one of the platforms I will talk to you later. And in this case, we have for certain of the components, we have a description of which is the technology that they are using to implement these elements, and we have mentioned to Kafka, to Unity, and to other tools that they have employed for building their architecture. And here, finally, we have an architecture for cyber physical systems, in which they have the physical in the left, which is represented there by a robot, the data. Well, all this architecture we can find, we can map to these five elements that appear in the architecture that I showed you in the beginning by Tao. Well, with respect to fields of application, as any kind of model, digital twins can be applied to many fields. You have there some of the most important fields for digital twins. First, manufacturing. As I said, it was one of the main fields of application of digital twins, where you can find a lot of publication on that field. They're used for monitor machinery, for predictive maintenance, for a lot of things. The reason is the problem that we have very good models for this kind of physical element. We have very good models for their behavior, for predicting when they will fail. So we have very good model for this kind of system. So it's easy to build a digital twin for that system. Another interesting field of application is that of smart cities. They are very complex systems, so we can build some kind of digital twin on them. We can do things related to traffic flow, to the use of infrastructures, or the use of energy. Also in the field of electronic health and healthcare, there are data to simulate patient health scenarios, to simulate organs. The reason there is that, doing experiments with the physical part, with a human or even with animal models, is first very costly, and then is risky and has moral issues behind it. So if we can develop any kind of model of an organ or for a patient for trying to view which is the best treatment for a particular situation, it has a lot of benefits, especially if you are considering personalized medicine. So it's a big field of application too, and also in systems in which security is very important, like in this aerospace or in automotion, that we can use these twins to test performance or design changes in the system. Of course, there is also a review in the literature about the different fields of application. They have this in this table, which are the twins that we have found in each of these fields, and manufacturing is the most prevailing. Some of these applications, okay, I have prepared this part a couple of weeks ago, but the other day when we went in the observatory, and the guy there explained that they were involved in a project of monitoring geostationary satellites, not only because they wanted to preview the risk of collision between them, but also to avoid the problem that caused to the observatory that satellites passed through the focus of the telescope when they're doing their work. Well, this is not a data twin, this is just a monitoring system. They don't interact, they don't send information back to control the satellites. But this gave me the idea, okay, let's find which are the data twins that may be present in this astrophysics field. And I prepared this slide yesterday, and I found quite a few interesting projects about projects and actual realization of twins related to astrophysics. First, both from the NASA and from the European Space Agency. First is the digital twin of the James Webb Telescope, which is the biggest telescope we have ever built and sent to the space. And they made a digital twin for the deployment process of this telescope, which is a complex process. Once in the space, the telescope must be deployed, and any problem during this deployment may cause the system, may cause all the vision to fail and to lose all the investment that they have done for doing, and all the time they have done for doing this project. So they developed a digital twin for addressing possible troubles that may happen during the process, and this digital twin process 800 million data items per day during this deployment process. We have also a twin for the OSIRIS-REx project, which is probably you have heard of it. It's a project of the NASA for going to an asteroid and taking samples and sent back to Earth. In 2023, the first mission of this project went to this Bennu asteroid, which is there in the picture, or the representation. I don't know if it is a real picture. And it's scheduled, if Trump allows, if schedule another mission to the asteroid Apophis in 2029. And the purpose of these twins are for helping the spacecraft to move in a microgravity environment, because these asteroids are fragile. First, you cannot go if you try to land on them to take a sample. You cannot go too fast because you may broken the asteroid. They are unstable, they are not solid, so maybe you have problems when posing on them. So it's very important to do a very smooth landing in the asteroid to avoid the failures in the mission. And the problem is that although these asteroids are small, they are fairly big compared with the spacecraft. So they have a microgravity that must be considered when doing these operations of landing. And also because they are not spherical, they are regular, this microgravity is not the same in all points of the asteroid. So it's a very complex operation, and they have to adapt to circumstances that cannot be foreseen when planning the mission, and also responding to uncertainties of what may happen at a given moment. These two projects are from the NASA. I have also a digital twin from the ESA that have developed this digital twin Earth. There's not a digital twin of the whole planet with all its features, but only an abstract, a very high-level representation of our planet, and it's used for monitoring and forecasting natural and human activities to visualize environmental changes, support climate policies, and improve resource management. And of course, like any other in this field of application, there's a review that talks about these twins and a lot more, so I will include the reference in the bottom of the slides. We have digital twins for related to energy. This one was developed by General Electric for windmill farms. And this is a composed twin because we have twins of each one of the wind turbines and also a digital twin of the whole plant. So this is an example of a composed twin. Also in the field of energy we have this product by Siemens, which is a digital twin of Finland's electricity network, which is represented here in the right. The network is not very complex, probably compared with other countries in Europe, because the population in Finland is small. But you can see that, okay, apart from the network itself, we have in the nodes we have the production and consumption centers, and this field of energy, of electric energy, is a very complex system in which we need to react very quickly to problems or to imbalances between the production and the consumption of energy. They have to be always balanced, and always means that every millisecond the consumption, the production of energy must be balanced, because we have very few means to store energy. So you are producing more energy than is being consumed, or to put energy in the system from a battery. No, we don't have big batteries for nationwide consumption, if for any reason the production goes down. So it's a good example of a system in which an automatic control system for a given system in this case could give a lot of benefits. We have also for oil and gas plants like this of British Petroleum. And for manufacturing, we have also a complex twin developed by Airbus for an aircraft manufacturing plant, in which they have not only twins of many of the parts that is in the plane, but also a digital twin of the whole manufacturing process. And okay, Tesla is not very popular nowadays, but they claim that they have a digital twin of each of the cars they sell. For if you have a Tesla, they have a digital twin, a digital shadow of your Tesla. They are continually send information from your vehicle to the company. We don't know what that Elon Musk does with all this information, but anyway, they can do things to improve the security of the cars, or to improve the maintenance. More examples in other fields. In agriculture, there are twins for doing farms and animal welfare, irrigation, resource usage, machinery, crop yield. You have there in the bottom a review on the literature on this field. In smart cities, which is a field I'm interested in, as I show you later, there are called urban digital twins, and they are used for urban planning, for monitoring the use of city infrastructures, traffic, energy consumption. Healthcare, we have also a lot of things, going from monitoring chronic patients to making data twin of particular organs like heart, kidneys or lungs, for training surgeons, for optimizing hospital operations and workflows. There are many twins dedicated to this area. And in our field in information and communication, there are also twins. There are twins of network infrastructures, like this Ericsson site digital twin, and also twins for telecom sites, like this big European X6 generation project. You have information of all of them on the links. And okay, some advertisement. This is a digital twin that we have created in our research group in Malaga. We are interested in putting people in digital twins. Most of the humans appear usually in digital twins only considered as numbers in a statistical form, like let's say, which is the distribution of probability that a pedestrian goes to a crosswalk. There are twins that use this kind of information, or in manufacturing, which is the curve of getting tired of an operator, so it's more likely to have a mistake. So we have to give him a rest, or we have to change his position to do different things, so he doesn't get too bored. But we're interested in putting individuals, each one with its particular characteristics, putting them in digital twins. And for that we have a project which is this, including people in smart city applications, in which we use the smartphones that we always carry on with ourselves for doing everything, for building what we call a digital avatar, a virtual profile of the user, explaining their habits, their preferences, and in this case of this digital twin for people movement in crowds, for capturing their movements as a sequence of GPS positions, and all this virtual profile can be served to third parties on demand. It's stored in the phone, but it can be offered to third parties. So we have here in the picture the people that are moving around. It's one of with their smartphones, okay, and we have all this structural product for making a digital twin of the crowd. Well, there is a couple of references to our work in this field. And also, apart from digital twins, my research interests deal also with quantum computing. And a couple of weeks ago, while reviewing papers for a conference on quantum computing, I found a paper on a digital twin of noisy quantum computers, or the NISQ computers that they are available right now. And this guy had developed a parametric error model of a particular technology for qubits, for QPUs, which is the transmod qubit QPUs. And in that case, I'm sure that this is a digital twin. What they have is a model, and with this model they can predict several kind of things. They can predict what can be the errors. But first, there is not. They use historical data for developing their model. They are not using data coming directly in real time from the quantum computer for running their twin, and then they do not actuate on the system directly. They just do it indirectly. Say, okay, when I transpile, when I traduce your quantum circuit to be executed by the quantum computer, we take information about which is the best distribution of the qubits on the machine, in order to have less error. No? This is a paradigmatic example of many of the publications that are nowadays called digital twins. That no, they are just using models, maybe very good models, or they are using simulators, but they are not developing twins. It is one of the consequences of this hype that, as I mentioned in the beginning, that there are many people that now are moving the titles of their papers to include the term digital twin, because it's now fancy. Mhm. Okay, in order to be finishing, with respect to different challenges, there are now many industrial initiatives for building twins. I've shown you some of them. Most of them are developed in an ad hoc manner. There is a lack of software engineering tools for development. There is a lack of standards. There is a lack of methodologies, a lack of frameworks, a lack of tools. Tools for data fusion and data curation. Data may be incorrect and we have to amend it, or we have to select the data which is valid for running our model. Also problems that have to do with interoperability between twins, and I will try to say a little more about composition and deployment, and also about validation and evaluation of digital twins. We have found efforts in all these fields, but not clear outcome yet. And of course, there is also a state-of-the-art or review report of research initiatives and challenges in the field of digital twins. And I would like to talk you about three of these elements. First is the composition of digital twin. I'm going back to this project of urban digital twins, integrating people, integrating citizens through these virtual profiles or virtual avatars. We have another case study, which is the public transportation system in the city of Malaga. And we have developed a digital twin of this for the bus system there, the public bus system there, and we have developed a digital twin for that also, using information coming not only from the bus system, because they have a lot of information on where each of the bus is. They can also know when a particular person, because they use electronic card for paying the bus, when a particular person gets into one bus, but they don't know where this person comes from before catching the bus, or when it comes down, because you pay at the beginning but you don't make any kind of transaction when you are descending the bus, so they know when you are leaving, and they don't know what you're leaving after. If we combine this information with information coming from the smartphones of the people, we can obtain a very much precise picture of movements of people in the city, and also information of interest to the company, for instance, for deciding to extend a certain line if most of the people of the coming from the bus walks in the same direction for 500 or so, 500 meters or so. Also, something that we have done in this field in cooperation with our colleagues in Extremadura is deployment twins in the digital continuum. Twins are not, digital twins not are necessarily monolithic. They are not deploying a single server. In that case, a study of public transportation, we have several nodes in which we could deploy the information. We have information which is based on the cloud, for instance, weather information that may influence on the use of the public transportation system. When it rains, people is more likely to take the bus, and that when it's a sunny day and they walk. We have the information which is in the servers of the bus company. They have all the information about where the buses are and whatever. We have also the buses and the bus stops that they are in fact equipped. The buses are equipped with a computer, and we can process some of the information there in the buses. And of course, in the last level, we have the information coming from the smartphone. So we have a deployment of the digital twin in the whole continuum, and we have to solve where is the best place for deploying certain of the functionalities of the twins, and also to decide how to communicate the different layers, and also how to implement and distribute data lake on this system. Okay, and I'm finishing. Finishing. Okay, we have also related to assessment, to validation assessment and fidelity assessment. We had also done a work in Malaga as a PhD thesis from one of our colleagues, Paulo Muñoz, and he wants to determine if a digital twin accurately represents its physical counterpart. The problem, the more general problem is the same that saying, okay, we have two models of the same system, 1 minute only. Two models of the same system, how can we find the distance between them? For that we use what we call the least distance, which is a person is walking on a straight line and the dog is moving around. We can measure the distance at any moment between these two traces. And this is a problem that's related with fidelity. We can model our system, our rabbit, with different degrees of fidelity, with different grains. And it depends on our purposes, of course. And okay, in the picture is Paula. This is we have a case study of an elevator, and in the company that manufactures elevator, they have very good models of the elevator. They have dynamics and kinematics models of the elevator. So what Paula did is to jump on one of these elevators and measure its movement. Her laptop here, which is the digital part of it, we have the physical part of the elevator, and Paula, which is trying to synchronize both models. And the problem seems trivial, but it's not so trivial. There in the upper part you have the model, and this is what predicts the model of the acceleration of the lift was going up and down. But then in the bottom half they have the reality, and you have to synchronize. You cannot just measure the distance at the same time, but you have to synchronize which are the correspondences between them. This might be trivial for a human, but it's not that trivial for a computer system. So we use the Needleman-Wunsch algorithm that's used to align proteins, and then he was able to solve this problem. And this is just an example of what can be done in research in this field, more than just saying, okay, I have developed a twin of this field that is just developing. No, there are also big opportunities for doing research in this field. And with this, I finish this part of the presentation. Thank you for your patience. And okay, I think that we now go for the coffee break, and we can have time for answers, for questions and answers after the second part. Thank you very much.
Thank you for the nice presentation. I think before we go to the coffee break, are there any open questions? Yes.
Thanks for the nice talk. In the very beginning, you talked about synchronous situation and communication between the digital and the physical twin, and in the end you came back to it because this is due to asynchronous things. Is it really important for every kind of digital twin? I understand when it's something like an elevator or a production pipeline or maybe even a spacecraft, synchronous information is okay, but when I think I have a digital twin of a bigger, maybe socio-technical thing, it makes no sense to have it synchronous, right? So has it to be synchronous always?
No, it depends, of course, it depends on the field of application. And we talk about synchronicities, suggesting that they have to be updated as close to real time as possible. But it's not really synchronous communication, because you're going to say, okay, I send you a message and until I have a receipt, and then you can get the message and get blocked. So this is why there is not in the middle. We have this data lake, which acts as a desynchronizing element in the end. So the idea is, depending always on the field of application, we have to be as real time as possible, but no, there's no need of a strict synchronicity.
Are there any other questions? Because I have one. Imagine I have companies that collaborate across different countries. Mm-hmm. How can I ensure that the data that it shares is compliant with the country's laws?
Well, legal issues are always very, very difficult. At least I guess that if you are in the European Union, there's a common law schema for sharing this kind of information. But if you go to work with someone in the States, or even if you try to get something done with China, that will be a very big problem. So this kind of composition of twins and sharing data between different law spaces is a very big problem. is related to one of these issues that I mentioned that are related to everything has to do with data fusion and also data curation. That was a big problem on legal issues with data, and in particular if you use personal data. Thank you for the question.
One last question and then 15 minutes.
Thank you. On your slides, when you showed different examples of architectures of digital twins, one of the slides was about architecture of digital twins in cyber-physical systems. And I was wondering, so a digital twin by default means a cyber-physical system, isn't it? So, is there a difference that you see?
There are many fields of applications. Many of them have to do with physical systems, so they are CPS, all of them. But also some of them have to do with social systems. If you put people, some of them have to do with e-health. So not everything has to do with a physical element that we want to model and we have to sensorize. So it's one of the big fields of application, but it's not the only one. You can make a data twin for any kind of process, a computer process. You can measure the computer process, you can sensorize it, and you wouldn't say, okay, it's running on a computer, but you wouldn't say this is a cyber-physical system. Cyber-physical system, I understand that there's something that you have a collection of physical elements that you are sensoring, like in a manufacturing plant or in a spacecraft or something like that. It's one of the big fields of application, but it's not the only one. You can model everything and you can make digital twins of everything.
Okay. Now 15 minutes coffee break, see you in exactly 15 minutes back.
That's why I asked about
Die ist dann in der nächsten
Yeah, because,
Gott sei Dank.